And you get 30 marks in this section. Remember when we started this semester, we said that this whole chapter gives us a big overview, or an overview of everything that we effectively going to cover in the textbook. And one of the first things that we discussed, we said that if you consider a computer system, now remember, a computer system is more than just the hardware that we have. And a computer system actually consists of 4 different components. One of them is the hardware, the other one is the operating system. Then you've got application programs, and the other are users. Those are the 4 components. Hardware obviously provides basic computing resources, CPU, memory, and I/O. The operating system basically controls the resources necessary for application programs. Our application programs define the way in which these resources are going to be used to solve a problem, word processing, and so forth. And users are the people that actually use the system. Remember, in your environment, typically your personal computer, only you use that personal computer, but computer systems in general support multiple users at the same time. So that's the first thing that you needed to remember. Next thing is, if we look at just from a way in which a computer program executes, and we consider the different hardware components involved when a computer executes, we can use this diagram to understand what might be happening inside the computer. The first thing is your memory that's in your computer contains 2 things related to an application. First, it contains the code and it contains the data. Your CPU has to go and fetch an instruction from the memory to execute. When it executes and does certain things, then sometimes it has to, let's say, write or read a file from the disk. What happens at that point, the CPU goes, in this case, to any one of these controllers. So your hardware typically connects via some kind of general controller, either a disk controller, a USB, or a graphics adapter, but effectively it's just a bunch of controllers, and the CPU goes and asks that controller to do something on his behalf, like fetching a file, getting some data maybe, or writing a file, and then that data is then transferred from the disk controller by the CPU to the memory over this thing called a bus. So the thing that connects these various hardware components together is what we call the bus of the computer. It's used for transferring data and instructions, transferring things across the network, across the different components. And that's how your system effectively executes an application. Very, very short. I think it goes together with this. Really, just the example explanation here. Your IO devices, the CPU can execute concurrently. Each device controller is in charge of a particular type of device. Each device controller has a local buffer, so that when it has to write or read information from the specific device, it uses that local buffer to protect memory. The CPU moves the data stream from the main memory to the buffers that's on the disk or on the various controllers. I/O is from the device to the local buffer of the controller, and then from the local buffer is taken to the memory. Right, I just mentioned also the last step was there is a device controller that forms the CPU that has finished its operation by causing an interrupt. And then as a side note, and this was mentioned even last week where we discussed what is a bit, and what is a byte, and what is a word. And it's important for computer science 3D students to understand the relationship between different pieces of memory and how that relates to your computer. Okay, bit is obviously a 1 and a 0. 8 bits is a byte. Why is a byte such an important thing to remember? Because that is typically the smallest chunk of data that you can store in your computer. Each memory address bigger, not smaller, 1 byte. And that's why we typically transfer things in your computer in things such as bytes. However, when we work with data, it depends on, and also instructions, so by the way, it depends on the architecture of your computer, that informs the computer of the number of bytes that we are going to use. For instance, the EAX, EBX, ECX, and EDX registers that you guys have been using so far in assembly language, those registers on a pure 32-bit computer are 32 bits in size, meaning 4 bytes. And that is called then the word. So on a 32-bit architecture, 1 word equals 4 bytes. On a 64-bit architecture, it means that there's 8 of these bytes that makes up the word. Okay, and obviously your registers, they grow in size. For instance, RAX is the 64-bit version of the EAX register. Okay, so it's important that you have to understand these different sizes and terminology. Okay, this brings us to storage. And one of the first principles that you have to understand is that not all storage are equal. When we look at a typical computer, we can basically have a hierarchy of storage that we can map against our normal computer. Now, forget about this last one, because our normal computer typically doesn't have an optical disk anymore, doesn't have magnetic tapes anymore. But the principle that this little pyramid wants to describe is that the lower we get into this hierarchy, the more data we typically have per cost unit, but also typically the slower it gets. The higher we go up in the hierarchy, the smaller it gets per cost unit, meaning if we want to buy a piece of cache memory, it costs significantly more than, for instance, the RAM that you have in your computer. Your hard disk, for instance, is a lot cheaper than the RAM in your computer if you map that against the storage space in your disk. What is important for you guys to understand is that data flows between these different levels. For instance, let's consider a problem. I'm executing an application. So I have to go, here's my CPU. The CPU has to go and load that program from the disk. So it goes to the device controller and then fetches the disk from the hard disk, or the program from the solid state disk or the hard disk. And then what happens with that instructions? Where does it go to?
Main memory.
Into the main memory. So from the solid state disk or the hard disk, that instructions goes into main memory. Now that it's in main memory, your processor wants to start running the instructions. So it says, I want to go and execute instruction, the first one that's in my address. Let's say this chair is address number 1. So it goes and fetches that memory. What happens then with that instruction? Where does it go to? It gets cached. Well, the first thing that your computer does, it first checks, is that thing already in cache? If it's not in cache, it then goes fetches it from the main memory, loads it into the cache, but then also loads that instruction into a register. Without that instruction going into a register, your processor cannot run it. Now at this moment, with the tracks that you've been doing, you know that there's the instruction register. The instruction register, or the program counter as we call it in the rest of the textbook, is the register that shows you where we're going to fetch our new instruction. But the instructions themselves, they go and also live into registers, but those registers are hidden away from us. We as assembly programmers, we don't have access to those registers, but they are still registered. It is impossible for your CPU to execute anything if that instruction isn't in a register in the machine. You can even go, but the same happens obviously with data. If you load some data that's in a database, where does the data reside in this hierarchy?
Android.
Where? Yeah. It's either the solid state or the hard. Both of them are the same type of thing, so you can decide whichever one. So let's say for that database, it's a normal server which doesn't have solid state memory, or solid state storage. So let's say it's on a hard disk. That's where the data is in the database. It then flows from there into the memory of your computer. Now that it's in the memory, if you want to go and calculate the sum of some of this data, what needs to happen with that data? Where does it then go into? Again, it has to eventually end up in a register somewhere, into either EAX or EVX, because that's in your assembly programming. You have done these things. You have said load something into EAX, and then add blah 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 EAX. And without that, you cannot add things together. It has to use the accumulator register and all of these things together. However, to speed things up, it creates a copy of that in the cache. So that when it has to get the next set of data, it doesn't have to go all the way to the memory. Yes?
So the science requirement when you need CD individual.
When you do? CD in region. Oh, torrent downloads. I don't know. No idea.
If you reach your CD is quite close, it's fast. Okay.
I can't comment. I don't know how that works. I've been a pirate long time ago, so I know. So yeah, but effectively to understand this principle that not all storage are equal, but effectively in many cases in our normal day-to-day operations, we touch on many of these layers, understand how these layers are influenced when we run applications, when we work with data, and so on. Right, just talks about the whole caching principle and remember when we talked about this section, this diagram, we said that the CPU, and I think it's mentioned in this slide as well, the CPU moves the data to and from main memory and the local buffers. So when we are reading or writing a file, the CPU takes the stuff from memory and loads it into the disk controller. Who does that? The CPU does that. Extremely inefficient. Byte by byte. Go take this byte, load it into the disk controller. Take the next byte, load it into the disk controller. Take the next byte, load it, or word, or whatever. It is not efficient at all. So what happens is that most of our controllers, our device controllers that we find in modern computers, they support what we call direct memory access. Direct memory access, it effectively means that we've got the role of the direct memory access is that the CPU goes and programs the direct memory access with the instructions to go and fetch and copy a certain set of data between the actual device and the memory, or the memory to the device itself. It's kind of like a little helper in your computer that is responsible for doing that transfer. And the interesting is that eventually, when the transfer is completed, then an interrupt will be generated, and they say per block, because that's how you program. You say take this block of code and write it in there, or read it from there. Typically it's not the whole file, but blocks of code. Then it will be interrupted and the CPU will have to intervene again. Okay, now take the next block, take the next block, but it's a lot, those blocks are significantly bigger than your individual words that you have to copy to it. So when you look at your computer, and I had a motherboard here, right? On that motherboard there was one chip. That is, chip itself, just by looking at it, doesn't inform us how many cores they have. Modern computers can have multiple cores inside this one chip. But each core is a fully fledged processor on its own. So if you look at an actual computer and you know that that computer has single core CPUs, but you physically see in the computer that there's 2 CPUs, then you will, when you open that computer, you will physically see 2 CPUs itself. Otherwise, a core is effectively a component that you will find inside a central piece of processor device, the die. Okay, that is the important stuff for chapter 1. Is that all? Yes, that's all. Chapter 2. Moving on. Okay, guys, so chapter 2 was all about operating system structures, what do we use operating systems for, and so on. And we started talking about some of the services provided by operating systems. And the services provided by operating systems actually is quite a lot. There's a user interface service. So how do we interface with the computer? Well, the operating system helps to provide such a service. This can be in the form of online interfaces, graphical user interfaces, batch programming, whichever way there's a user interface component. Operating systems helps us with program execution. It allows us to load a program into the memory of the computer and start running it. It handles the I/O operations for us. It does file system manipulation, so we copy files from one place to the other, renaming of files, creating files, those are all system manipulation. Handles the communication, so typically when we handle the sharing of data between processors or processes. We've seen this now in chapter 3. That's sometimes a lot of the responsibility belongs to the operating system for that. It handles error detection. So those are some of the user presented features, and then there are also other features that specifically just looks at managing of resources, so resource allocation, the accounting, protection and security. Those are some of the other features provided by the operating system. Right, this brings us to system calls. What is a system call again? We discussed this today already. So whenever your computer works, we have this principal idea that your operating system is broken up into 2 levels, or 2 modes. One is called user mode, and the other is called kernel mode. And when we execute code in user mode, that code does not have access to any of your system resources directly. You have to work through the operating system for anything in user mode to access the system resource. So you can only access system resources indirectly, and the way that that is done is through system calls. So you basically can create system calls for many different purposes, and you can actually go and look at all the different types of system calls that you can have here. So creating of processes, file management, device management, information management, communication, etc. Those are all the times when your system uses a system call. So if you just look at this as an example, your textbook has a nice example where they actually have such a command that when all the different system calls, and a typical instruction when you copy the content from one file into the other, look at all the different system calls that potentially can happen in just that one program. So can you identify things that can create system calls? You know where they go to, and who are, and when does your computer typically create a system call? That is important. Right, let's see what else. Obviously, there's different ways. When you run a system call, in many cases you've got a function in user mode that's got certain parameters, and those parameters need to be passed to the kernel. And there are different ways in which we can pass the parameters from a function call into a system call. And the ways in which this is done, there they are. The simplest implementation of this is purely just putting some of those parameters into registers. That's a very, very simple way of doing it. Basically, you just put something in there, say EAX or EBX or ECX, and then you do your system call. Your system call function will then be fetched from there. Another approach is where you create a block of memory, and in that block of memory, you declare basically declare your different parameters, and then the address of that memory location you pass and make it as part of one of the registers. Another option is where you push your parameters onto the stack by the program, and then your system call itself will just pop it onto the stack. Right, so those are the three main ways in which you can pass your different parameters in your system calls. Right, and then when we get to the different operating system design, we've learned that operating systems can be designed using different principles. You get what they call a monolithic principle, the whole microkernel principle, and then there's also layered principles, and then obviously there's a modular principle as well, which we discussed in this chapter. But if you think about the layered approach basically says that when you introduce a function, and that function is dependent on another function, then the other function must be a layer lower than the other one. So your dependencies basically flow through these different layers. So a layer 2 code will always be dependent on a layer 1, and a layer 1 will obviously have access to the kernel, or the layer 0, which is the hardware, and so on and so on. So using that principle of dependencies, you can start designing some operating systems and the operating systems labels in your system. So understand that and know how to apply it eventually. And that's it. This whole chapter is all about processes. A process is a unique piece of thing that exists inside our computers. And this chapter starts by describing that processes consist of multiple parts. So if you ask me what is a car, for instance, then I can describe a car consists of typically 4 wheels, it's got a body and doors and stuff. A process is something similar to try and describe something like a car. So looking at the individual or the various components that typically make up a process can kind of describe what a process is. First thing is that a process consists of code. Without code, there cannot be a process. And we've also now learned in the next chapter, obviously, is that we can have multiple pieces of code that can execute simultaneously. But effectively, that is the program code. It's typically called the text section of your computer. So if you think about the memory of your computer, there's a text section of your memory, and then there's data sections, multiple types of data sections. But the text sections are, or text section is your instructions. Your current activity includes the program counter, that is a special type of processor to understand the program counter, and it consists of a number of registers. So each process has its own set of registers. In fact, already in chapter 4 you learned that actually each thread has its own program counter and set of registers. Each process also has a stack. Stack contains temporary data. It contains things as the return addresses and local variables. In the past, prac that you just did last week, you learned about creating this principal idea of a stack frame, which created the area where you could store your local variables. It has a data section, and the data section was the area that had the global variables, as you've also seen so far in your assembly prac. And then there's a section which we call the heap. So those are all memory types. If you think about all of these last things like the stack, the data section, and the heap, those are all different types of memory there. The heap obviously contains dynamic memory that can grow depending on like arrays that we create. Normally, things in the heap is also normally globally available through what we call pointers. Okay, let's see if there's anything else. Nothing here. Processes, when they run, or when a process exists, rather, let me put that way, there is a specific state that a process can be in. Most textbooks mention the three middle ones. This textbook also mentions that the process will also have a new state and a terminated state, which is fair, which is true. But typically, when you look at a process on your computer, it's either running, it's either waiting, or it's ready. Those are the three main states. Typically, when it's new, it's only there for a fraction of a few milliseconds before it starts running, and it's only for a fraction of milliseconds while it's terminated, while the operating system cleans out the memory. So, how does running work? Well, typically, running means we're actively running that process in the CPU. When we consider a uniprocessor system, uniprocessor means only one CPU, one core in our system. Only one process can execute at a specific time slice. While that time slice is executing that one process, all the other processes must either be waiting or ready. Ready means it's sitting in a queue, ready to be selected by our scheduler for the next time slot. It's kind of like you going to the Department of Home Affairs. No, that's probably bad. That's probably there's other things of you're in class and I ask a question and a bunch of hands go up. Then all of those students with the hands up, they are ready. I can ask any one of them. That's kind of what the scheduler does. All the other processes with their hands down there is waiting for I/O to happen, like trying to fire up the long-term storage or the short-term storage, or whatever they say. That's kind of the principle idea. So a process that's currently waiting is a process that typically the system calls to a piece of hardware, meaning we're communicating with the device controller, and the device controller is doing some stuff for us, such as writing a file to the disk or reading data from the disk. While it's busy doing that, that process can't continue. So the whole file read instruction has to wait for that instruction to finish before it can start working on the data that it was waiting. So it will go into a waiting state, waiting for I/O to finish. Once that I/O has finished, it will raise an interrupt, and that process will then move from waiting to ready. And now that it's at the ready queue, the hand will go up, but it's still not running because the scheduler hasn't selected that process from running yet. So that's the process states and how it will run. The way in which your operating system looks at processes and handles them is by keeping track of these different components of your process. And typically that is done in a data structure which we call a process control block. And the example that we have in the textbook, they actually show you such a potential process control block that shows like the process ID, the state, blah, blah, blah. But effectively, you can visualize it as this block of information that we have with it. And each block typically describes, first of all, what's the state of the process in. running, waiting, and so forth. It shows the process ID or process number. Each process that runs on your computer will have a unique identifier. It will have the program counter, meaning the instruction that is currently executing, the set of registers, the values of those set of registers, the memory limits of that process, the list of open files, and many other resource information associated to that process. So that's typically what you will find in such a process control block. You have to know what these things mean and how they affect your computer. Okay. So next, let's talk a little bit about parent and child processes. Now, I must be honest, this is things that it happens in Windows as well, but it happens more often in Linux operating systems, because with Windows, in many cases, the parent process will create a child and then the parent kind of dies, and then the child will run on its own. But in general, in operating systems, when processes terminate, the following will happen. So you've got, in a Unix Linux environment, you always have a parent process with some kind of a child process. And when a child process terminates, meaning it's finished running, it says, I'm exiting. So typically there's an exit instruction. Show it here? Yeah, talk about it. Exit instruction, if you can remember for C++ in your first year, you had exit, then that stopped the process from running. Or you can stop the process from running by the return instruction in your main function. That basically stops that process. That starts it, okay, I'm finished now. And then it goes into the system call, and the system call has to then clean up the memory. Now typically when such a process exits or terminates, the memory obviously is given back, so the operating system goes and says, give back the memory, but because we can exit certain specific error levels, so error numbers potentially explaining how did that process exit? Was it a graceful termination? Was there perhaps an error termination and so forth? That information is kept in the operating system so that the parent process can then later on read that. And the parent operating system will typically have a wait instruction like this, and it will then, the parent process will be able to wait until that process terminates and then get the typical status information. However, if the parent process does not have or hasn't got into that line of code that has the wait instruction, meaning the parent process kind of ignores, I'm not waiting, the operating system has to still keep that child information in the process list about how they terminated and so forth. And in that case, we call that a zombie. So the child has terminated, but there's still some residual process information in the operating system because we're waiting for the parent process to go and terminate and read the status information. Once the wait has obviously the wait instruction ran, then that information gets reclaimed and the operating system then does totally scrap the child process. But if it's not, if it hasn't run the wait yet, it's called zombie. It is also possible for a parent process to terminate. No more parent process. And then the child process now terminates. Who does it report its exit status to? In that case, we call that an orphan. And typical other operating systems have different ways in which it handles that orphaned process. One way in which it does it is that it assigns a new parent at that point. So it's kind of like a step parent. And then only it does it fully terminate the little residual information that's still stuck in the operating system. So an orphan process is where the parent terminated without executing the wait. Right, so just understand that. And then last thing, when we look at remote procedure calls, remember we said that processes can communicate with each other using different mechanisms. And we So there's two general models. One is a memory shared model, the other one is a message passing model. And then later on we say that, but we can also have processes communicating across different computers. And one way in which that happens is through what we call remote procedure calls. But with remote procedure calls, there's certain problems that we have to consider when the operating system builds in remote procedure calls. Protocols. What's our time with that? 10 more minutes. This is the last time. Another time. Anyway. So with RPCs, in the RPC protocol, they have to consider the problem of ensuring that messages are delivered exactly once, or at most once. In fact, RPCs actually rather make use of at most once. But what does that mean? And we had this principal idea where we had two processes. I don't know, there's one here and there's another one. But let's consider a process A here and a process B there. Process B communicates with process A, sends some kind of instruction across. Process A basically keeps track of that specific instruction, maybe some time stamp that was sent by the instruction to know I have now received instruction XYZ that was sent by you, process A or process B, at, let's say, time stamp, something like this. And it says, okay, I acknowledge that I have received this instruction. The reason why they do that is because remember, when this process B sends instructions, it has no control over what happens on the network. Some processes can be duplicated, or some instructions or messages can be duplicated and following different paths. And when they get to this computer here, it can be duplicated. So how does this process know that it doesn't duplicate these instructions? Because that can be fairly bad. And in certain scenarios, it can be quite bad. So consider these scenarios about when are things, if they get duplicated, it can be fairly bad. So how does it work? Well, it keeps track of potentially instructions that were sent, and then it says, I've already received you, I'm not going to execute the duplicate that I've just received. So there must be some kind of mechanism that's called exactly once. Now, at most once basically means that when an instruction is sent, or an RPC instruction is sent, there must be some kind of instruction going back, saying, I acknowledge that you have sent it. And that ensures that from the sender's perspective, I know that my instruction was executed exactly once. Those are the two differences. The one is from the sender's perspective, the other one from the receiver's perspective. And it is important to build these mechanisms specifically for RPC. We typically want to have most ones, but understand what exactly once also means and the effects that they can have if you don't introduce it properly. So consider the problem about duplicated messages or messages getting lost or that kind of thing. Know how that affects your system. And that is the last thing that I wanted to revise. So just a reminder again, question 4, we already discussed this. 10 marks, your conversion between the different numbering systems. Again, focus on the shorthand binary conversion. So converting from octal into hex. Converting from binary into octal, converting from binary into hexadecimal, converting from octal into binary, converting from hexadecimal into binary. Please use we've got a little table that we normally draw. Use that mechanism as the easy way of doing it. And then obviously question 5 is the assembly program, everything up to and including last week's problem must be considered for that. And that, ladies and gentlemen, is today's revision.